Today, it's a great pleasure to have Strominger from Harvard. He very kindly agreed to change the timing of his talk and deliver what is now a joint science and physics and astronomy colloquium. So Professor Strominger is a famous guy. He's one of the field. He speaks fluent Chinese. He spent some time, I don't know whether he was still at Harvard or he had taken some time off Harvard to spend some time in a commune in China as a journalist there for a while. So that already tells you something about the kind of, anyway, the reason he's here is not because he speaks Chinese, but because he made fundamental contributions to theoretical physics. Through his career, he was undergraduate at Harvard, and he was a PhD student at MIT, then he was a professor at consultant at Harvard, and then for 97 years here at Harvard, where he's now the director for the Center for Fundamental Laws of Nature. Really, the list of his accomplishments is too numerous to really condense, but among them is the demonstration that really string theory can serve as a unified theory of all fundamental forces, using this idea of called Radial quantification. So it was one of the heroes of the early days of string theory, and then he has done many contributions both on mathematical and more physical evidence of string theory. He was one of the pioneers in using brains, solutions, and then used dualities, the brains, and some mathematical contribution to mirror symmetry, Walsh transition in string theory. But I think, you correct me if I'm wrong, but and his main interests really are in conceptual questions of quantum gravity. With or without string theory, I think there will not be much string theory in today's talk. And perhaps his most famous contribution has been this groundbreaking work with Papa in 1995 on using brains again to count the number of black hole microstates. And he's done many other things, again, this is too numerous to mention, and today he will tell us about some new ideas of what is in all subjects, several subjects, and asymptotic symmetries in space-time and how they connect and help resolve puzzles.
Thank you for the kind introduction, and it's a pleasure to be here giving this talk. So I am going to talk about a picture which has emerged over the last 3 years involving an exact mathematical equivalence between 3 subjects, each of which had been studied extensively in parallel for roughly half a century, and a kind of triangular equivalence. And identifying these 3 subjects as equivalent has led us into all kinds of surprising new insights. So did I do that? No, okay. So what are these 3 subjects? Well, one of them is the so-called soft theorems in quantum field theory, the first examples of which I think go back to the 30s or something with Bloch and Nordzik and Francis Lowe in the 50s. The modern version, the way we think about them now, was spelled out by Weinberg in the 60s. So it's a very old subject, and it's a kind of foundational structure in quantum field theory. No computation involving any kind of LHC cross-section or anything would even make sense without these so-called soft theorems. And what are they? Well, they tell you that if you have, one example would be if you have a scattering amplitude where you have some incoming particles and some outgoing particles, and let's say one of the outgoing particles is a photon, and then you consider a limit in which the energy of that photon is taken to 0, there's a peculiar relationship which says that the resulting scattering amplitude is equal to the amplitude without the photon times the so-called soft factor, which Weinberg wrote down. So these soft theorems are ubiquitous. They basically occur whenever you have massless particles. Now, the second subject is asymptotic symmetries. Now, this is kind of a funny word because when you say asymptotic symmetries, you might think I'm talking about symmetries which are only exact symmetries in some limit. But in fact, asymptotic symmetries are exact symmetries, just like all the symmetries we usually talk about. The word asymptotic comes in because they're symmetries which are most simply described in terms of the description of the physical system in the far past or in the far future when everything has dispersed and settled down into outgoing waves or particles. And there was famous work on this done by Bondi, Vanderberg, Metzner, and Sachs in special relativity. The asymptotic symmetries consist of rotations, boosts, and translations. And Bondi, Metzner, and Sachs wanted to show that somehow in general relativity you could recover it in an appropriate limit. And they spectacularly failed. They found instead a much bigger infinite dimensional group. And this is something which relativists have been wrestling with for the last half a century, and I think we now have some insight into how to think about it. But these asymptotic symmetries occur in many other instances, and I'm going to talk about asymptotic symmetries in quantum electrodynamics today. The simple relationship here is that whenever you have a symmetry, you have a so-called Ward identity about quantum mechanical matrix elements, and these soft theorems, as far as we can tell, can always be understood as related to symmetries. So this relationship between the S matrix elements has recently been understood to be a consequence of symmetries. And then the third leg here is the so-called memory effect. The one that has been studied the most is the gravitational memory effect, where if you have, say, a passing gravity wave, everybody's been talking about LIGO recently, passing gravity waves, the mirrors oscillate, and then after it passes, well, they're on pendula, but if they were free to slide back and forth, they would not return to their initial position. So it's a kind of DC effect. And going back, and there are various experiments proposed to detect these memory effects involving pulsar timing arrays and so on. And the discussion of this started in 74, the detection of gravitational memories. And it turns out that the formula for gravitational memory is simply a Fourier transform of the soft theorem, or the formula for in general, the memory formulas are Fourier transform of the soft theorems. Now, this is a triangle which echoes throughout physics. It occurs, as I said, in basically has some version in any theory with a massless particle, but that's not all. Even within a given theory, for example, in QED, there's a leading soft theorem and a subleading soft theorem, and so even within each individual theory, there's different copies of this triangle. Now, I am not going to try to describe all instances of this triangle or give an overview of this. I'm just going to follow one little thread which led us to some observations about black hole information. So I'll talk about electromagnetism, some basics of this triangle. That'll be more than half the lecture, and then I'll give a lightning review of the black hole information paradox, and then I'll talk about ending on some recent work with Stephen Hawking and Malcolm Perry on what this has to say about black hole information. Okay, so I'm going to start with something incredibly simple. It's been known for 150 years. And this is the formula for the radial component of the electric field from a static point-like charge. Looks simple enough. Now if you boost it, and this formula has also been known for over a century, this is the Lienard-Wiechert field, with velocity v, then the electric field looks a little different. And this is the exact formula. This obviously is a problem which can be solved exactly. And the peculiar thing, which I suppose Maxwell must have known, but I didn't realize until the last few years, is that the radial component of the electric field is actually not well defined at spatial infinity. And this fact is going to be crucial to everything that I'm going to say, so I'm going to belabor it a little bit. So, in other words, it depends on what path we take in the xt plane to get out to infinite R. So I'm drawing now a picture of Minkowski space of a type that I'm going to be using throughout this talk. So I've drawn all of Minkowski space in this diamond here, and I've drawn it in such a way that light rays go at 45 degrees, and this is where light rays go to. This is where they come from. This is called future null infinity. This is called past null infinity. And when I do this, a particle moving with constant velocity, when I draw it this way, a particle moving with constant velocity never gets out to null infinity. Light rays will always eventually pass it. So it ends up here, and this is what a trajectory of a particle of constant velocity would look like. Now, if I take this formula on the preceding page, it's 1 or 2 lines of algebra to show that if I go up to future null infinity, like that, and then go back down to this point, which is spatial infinity, I get this formula. On the other hand, if I do the other thing, which is to go down here and then go up, I get this formula. They're not the same formula. There's a minus here and there's a plus here. Okay, so the electric field in standard electrodynamics. Okay, so the language I'm going to use here, I've got this symbol for this, but I'm going to call this the past of the future. And this is the future of the past. They're not the same thing, even in Maxwell electrodynamics. So the value of the electric field is different at the past of the future than it is at the future of the past. However, even though it's different, it's related. If I do a parity inversion, in fact, the value of the electric field here is equal to the value of the electric field at the antipodal point. And so the boundary condition that's implicit in Maxwell electrodynamics is that the radial component, the leading term in the radial component of the electric field at the past to the future is equal to the leading component of the radial, leading term in the radial electric field at the antipodal point. There's a sphere here. At the antipodal point in the future, the past. And not only is this true in classical Maxwell electrodynamics, but as we'll see later, or will be inferred later, this boundary condition is implicit in the I epsilon prescriptions that are used in the Feynman diagrams in quantum electrodynamics. Okay, so this simple observation immediately leads us to the conclusion that in any theory of involving an electromagnetic field, there are an infinite number of conservation laws. That is, things that if we know their value in the past, we can predict their value in the future. Obviously, if these two things, okay, so a notational device here, I define a function on the sphere, I define a function, epsilon, which has the property that its value at the future of past is antipodally related to its value at the past of the future. So I absorb that antipodal identification into this function, and it then follows that if I integrate the electric field over the future of the past, weighted by any function whatsoever, cosine to the 17th theta, sine 13 phi, whatever, and take it at the, compare that to what I get if I integrate the electric field at the future of the past, I get the same thing. Since this is true for any function, it's an infinite number of conservation laws. Now, let's suppose that we take a special choice, that epsilon is a constant. Well, then we can use Gauss's law, d mu divergence of F is equal to the electric matter current. And this just tells us something we're all familiar with, that the sum of the incoming charges, so we use Gauss's law and we write this as an integral over this incoming surface. The sum of the incoming charges is equal to the sum of the outgoing charges. That's charge conservation. But there are infinitely many more conservation laws on the same footing. So what are these conservation laws? Well, when epsilon is not a constant, well, we can still use Gauss's law and write this as an integral over the entire past. And what we get is we get an extra term. So first we get the sum over incoming charges weighted by an arbitrary function on the sphere. And the function on the sphere evaluated at the angle from which the charge came in. So that can't possibly be conserved on itself, by itself. So there's this strange extra term, and that's equal to the analogous thing computed in the far future. What is this strange extra term? Well, it's the integral over this. It's the integral over this entire surface here of a component of the electric field transverse to the sphere, contracted with the derivative of this arbitrary function epsilon. So I want to call that a soft photon. It has zero energy because it's time averaged, and with polarization d epsilon. And in this subject, the word soft is synonymous with zero energy. Okay, so so far we've just been talking classically. And so classically, this conservation law relates some arbitrarily weighted sum of the incoming charges to the same sum of the outgoing charges after we add in what I'm calling this funny extra term that is linear in the electromagnetic field. Now, let me jump to this one, why I'm calling it a soft photon. We can write this funny extra term as the limit as omega goes to 0 of e to the I omega v, where this is advanced time, dA epsilon FAV. Now, for non-zero omega, this is in a quantum theory where this will create and annihilate photons of energy omega and polarization dA epsilon. And so when the term, what we actually got in our equation was this thing with omega equal to 0. So we can understand that this thing creates and annihilates soft photons. All right. So I talked about a classical conservation law. What about in the quantum world? Well, in the quantum world, we have an S matrix. We start out with some arbitrary incoming state, bunch of incoming particles. Something very complicated happens. We throw them at each other. Computing this is a huge amount of work in general. And then we get some outgoing state. But what does it mean to say that there are, what is the quantum version of the statement that that there are conservation laws? Well, the quantum version of the statement is that we take, that there's a charge that commutes with the S matrix, or put another way, that if we take the charge and act on the in state and transform it, we get, and then evolve it with the S matrix, we get the transformation to linear order. This is just that law written to linear order. It's equivalent to just transforming the out state by the same conserved charge. Now, this relation, since this is a symmetry, it has to be true for any pair of states, in states and out states. And moreover, the last statement, if we had one relation that was true for every pair of in and out states, then we would say we had one symmetry. But we have one relation for every function on the sphere, so we have infinitely many symmetries. So what is this? So we found some general relationship between between any S matrix element, and it would be really just too incredible if, after QED had been around for nearly a century, that there was some new relationship between S matrix elements discovered. But of course, it's not new. It was known and derived basically by direct analysis of Feynman diagrams in the way that we think of it by Weinberg in 1965. Now, one could also reverse the logic. One could have started with the soft photon theorem, and this could have been said in 1965. One could have started with the soft photon theorem and rewrite it in this form, and deduce that there are symmetries of the S matrix. Now, actually, it's actually a lot of work it's straightforward, but it's many pages of tedious algebra to rewrite this. It's naturally presented in one form here, the way I've described it, and to rewrite it in the form that its standard textbook quantum field theory form is some lengthy algebra. Okay, Now, whenever we have a conservation law, we also expect symmetries. And so what are the symmetries? Well, all we have to do, say we look up at scribe plus, is to take this charge, construct the commutators, and it's not very hard to construct commutators at future null infinity because everything is weak out there. So perturbation theory is good. We don't have to worry about a lot of strongly interacting stuff or loop corrections. So we compute this commutator, and we find, lo and behold, that what this charge does when we commute it with the electromagnetic field is it generates a gauge transformation. And that gauge transformation is parameterized by an arbitrary function on the sphere. So now, we often say that gauge transformations are trivial. They don't have any, in electromagnetism, they're trivial. They don't have any observable effects. But that is only the case if the gauge transformations die off at infinity. So, my favorite example of this, I think the one where one can understand it the best, is in gravity. So there the gauge group is diffeomorphisms. So suppose we have a black hole sitting there, a short-shelled black hole, and then we boost it. Well, that's a diffeomorphism. We can write down explicitly the diffeomorphism that maps a static black hole to a boosted black hole. But we've changed its energy and its momentum. So that is a diffeomorphism which surely we would not want to say is trivial. So some diffeomorphisms and some gauge transformations act non-trivially on physical states. And here what we've discovered in quantum electrodynamics, or in any theory with an electromagnetic field, that there are an infinite number of ordinary abelian gauge transformations which act non-trivially on physical states. And they are parameterized by an arbitrary function on the sphere. And the effects of these can be measured. Now, they're parameterized by an arbitrary function on the sphere, but that function is antipodally related in the future to the one encountered in the past. So that is the subgroup of the electromagnetic gauge group which acts non-trivially on physical states. Now, so this has some consequences for the way we think about the vacuum in abelian gauge theories, in electrodynamics. So let's suppose we have a vacuum state which is annihilated by the Hamiltonian. Now the Hamiltonian commutes with all of this infinity of charges, Q. That's what we just showed. And so therefore, if we take the state 0 and we act on it with Q, we get a new state. And it's still annihilated by H. What did this operator Q actually do? Well, it took the vacuum and added a soft photon to it. And so it changed, for example, even no matter how soft the photon is, it still carries angular momentum. So this state 0 and this state Q plus epsilon on 0 differ by they have different angular momentum, and therefore they must be orthogonal. So these are not the same state, and in fact, there are infinitely many degenerate vacua which can be obtained when they all have different angular momentum. And so we can say, so it's simply not true in abelian gauge theories that the vacuum is unique. It has this infinite degeneracy, and we can describe that by saying that the quantum vacuum has soft, meaning zero energy, hair, meaning a distinguishing characteristic. Now, by definition, if you have a symmetry and you have a charge that generates that symmetry and it doesn't annihilate the vacuum, then we say that the associated symmetry is spontaneously broken. So this infinite symmetry group is spontaneously broken, and the action of the charge moves us among the states of degenerate vacua. And the thing that you get when you act with the symmetry generator on the vacuum is called the Goldstone boson. So in this case, we see that the soft photons are Goldstone bosons of the spontaneously broken large gauge symmetry. Okay, so everything I said goes through in a nearly identical fashion in gravity. And in fact, the gravity case, oddly, was worked out before the Maxwell case, because people had thought about this kind of question in more similar terms in the gravity case. So there's a Newtonian potential in general relativity which obeys a kind of antipodal matching condition, that its value at the past to the future is equal to its value at the antipodal point in the future of the past. There's an infinite number of conserved charges, so which generalize the energy. So we've had an infinite number of conserved charges in abelian gauge theories which generalize our usual notion of global charge, and similarly, there's an infinite number of conserved supertranslation charges which generalize the notion of the total energy. And these charges create soft gravitons in the same way that the electromagnetic charge creates soft photons, and the soft gravitons are the Goldstone bosons of the spontaneously broken supertranslation symmetry. Again, you can take this matrix element of this conservation law, and you find, after many pages of algebra, again, that it is completely equivalent to Weinberg's 1965 soft graviton theorem, which was derived using Feynman diagram techniques. Now, if you look at what symmetry this generates, it's a symmetry that was, as I mentioned right at the very beginning, it's the symmetry is the so-called BMS supertranslations, which are translations of the sphere that lives in the far future, but it turns out that you can translate different points on the sphere at different rates, and that is still a physical symmetry. These are the BMS supertranslations. Now, what's particularly nice about this is that the difference between the different BMS related vacua, one can, basically any physical process will, if you disturb, this is true both in gravity and the abelian theory, that if you disturb the system, since there's this infinity of degenerate vacua, in general it will settle down to a different vacuum than the one you started out in. And this was known, though it was never stated in the way that I just stated it, but it was really discovered by Zeldovich and Polnarov in 1974 and called the gravitational memory effect. And indeed, Sasha Jabodov and I showed that you just take the Fourier transform of the memory effect and you get the Weinberg-Soft graviton theorem. This is a bizarre instance in which gravity was ahead of the Maxwell theory. Okay, so that's the review of this triangle of ideas. Now I want to talk about what this has to say about the black hole information paradox. So here's a summary of a lightning summary of the black hole information paradox. So the idea is you make a black hole. If you get too much matter in too small of a region, according to the Einstein equation, the gravitational forces will become very strong and everything will collapse into a black hole. Then there is something called the no-hair theorem. And the no-hair theorem is a correct mathematical theorem, but I'm arguing it was misinterpreted. The physical interpretation of it was incorrect. And the no-hair theorem was often claimed to show that after everything falls into the black hole, that it rapidly settles down in a time of order, the light crossing time of the black hole. The system rapidly settles down to a black hole, which is characterized only by its mass, its charge, and its angular momentum, and doesn't have any detailed information, doesn't have any detailed, no record is left of what went in there. And then, according to Hawking, and this is in a picture where we treat quantum effects as very weak, according to Hawking, a long time later, the black hole starts to evaporate, Hawking radiation comes out, and a very, very, very long time later, the black hole disappears. So what that is saying, so let's imagine, for the sake of argument, that there's information in the PhD thesis. And then we want to reconstruct, this was the only copy of the thesis, and we want to reconstruct it. Well, if this were just a fire, a big bonfire, and we threw all these things into the bonfire, we believe it is a central premise of physics for the last many centuries that in practice, certainly not in principle, certainly not in practice, we could if we went up here in the far future and we caught every last little light ray and every last little wisp of ash and we looked at the final configuration of the bonfire, and we had absolutely perfect knowledge of all the laws of physics, we believe that in principle, from perfect information of what happens up here, of the state of the system up here, and perfect knowledge of the laws of physics, that we could run the movie backwards, reconstruct the PhD thesis, and read it. And in other words, that the present, perfect knowledge of the present gives perfect knowledge of the past, and also perfect knowledge of the future. Now, it's easy to see that if you don't have, if you can't reproduce the past, it follows that you also can't predict the future. So, if this is correct, and this is what Hawking argued in 1974, the world is not deterministic. Now, that's a pretty serious thing to say. It's saying that we can't describe the universe by laws. And what are physicists supposed to do if we thought our job was to discover what the laws of nature are, but it's saying that there aren't laws. Now, you can't just at this point throw up your hands and say, okay, I give up. If you believe that determinism is not a feature of our universe, you need to come up with some other kind of probabilistic or statistical or something. You need to be able to say something about the universe. And alternatives to deterministic, everything should always be on the table, and maybe the universe isn't deterministic. If there was nothing before the Big Bang, indeed, it's hard to see how it could be. So maybe determinism is not exact, like other things we believed to be true and then turned out to be corrected. But nobody has come up with an alternative, and it doesn't seem like that is what is going to happen here. And indeed, I think when Hawking first argued this, many people found it compelling, but as people have thought about it over the years, over the last 40 years, of the hundreds or thousands of people that have thought about this, this paradox here, I believe there are now only two, or there are only two who have admitted to believing that what happens is that the universe isn't deterministic. And Hawking himself, long ago, said, I don't know how this works, but it doesn't seem like throwing out determinism is a good thing to do. Somehow there must be some way of reading this PhD thesis, even if it gets thrown into a black hole. Now, so either there's a flaw in the argument, or there's a flawed assumption. And what's new, so though we started these investigations from a different point of view, they have in fact led to the discovery that there are some flawed assumptions in this argument. The first thing is that it was always assumed that once the black hole disappears and completely evaporates, the system is settled down into a unique vacuum state, that the vacuum state in quantum gravity and flat space or in electrodynamics is unique. We now know that's wrong. There's an infinite degeneracy the vacuum is like a big hard drive, and it's perfectly possible that, it's not ruled out that there could be, that the final state of the vacuum could be correlated with the Hawking radiation in such a way that quantum purity of everything is maintained. So one flawed assumption was that the vacuum was unique. Another is the no-hair theorem, that there was no hair on black holes. And what the no-hair theorem really says is that all solutions of the Einstein equation, or the many variants of the no-hair theorem, but what one of them says is that all static solutions of the Einstein equations are equal to the Schwarzschild solution up to diffeomorphisms. That is a perfectly correct statement. However, the diffeomorphisms, the big ones, do not map one physical state into an inequivalent physical state. And therefore, it doesn't follow from the no-hair theorem that all black holes are the same. And indeed, if we were, and indeed there must be some, we can infer that there must be some mechanism for black holes to carry these charges, even the electric charges that I told you about, because if we took, if we had a black hole in our space-time and we used Gauss's law to fill in the surface, and there's a black hole there, we have to have a boundary term at the horizon of the black hole, or we either have to take the slice through the black hole. But in any case, there will be portions of the charge outside the black hole, and portions of the charge density can move in and out of the black hole, and there is no way for the black hole to be sort of impervious to such charges. Now, we're used to the idea that if you actually do the calculation of Hawking radiation and what comes out, you get that it's a thermal spectrum at the Hawking temperature. Now, a thermal spectrum of particles has some energy width, and that won't conserve energy exactly. So if it were really just exactly a thermal spectrum, we would violate energy conservation. Nobody thinks that energy conservation is violated when a black hole evaporates. So by hand, we put in a constraint that however much energy is carried out by some quantum of Hawking radiation, the energy of the black hole shrinks by a corresponding amount so that energy is conserved. But this will induce correlations between the black hole and the outgoing Hawking radiation. Similarly, with momentum, the Hawking radiation can have different amounts of momentum, but there's overall, we demand that momentum is conserved by making the black hole recoil whenever it emits a Hawking quanta in one or another direction. So these four constraints, we have always presumed we must put in as constraints by hand on which correlate the Hawking radiation with the quantum state of the black hole. Now, four constraints isn't enough to help with the information problem, because there'd be a lot of could be a lot of information in a PhD thesis, and just 4 bits of information won't take care of it. But now all of a sudden, we've got an infinite number of constraints coming from these infinitely many conserved charges. So just as the black hole must change its energy when it emits something with a given usual global energy, whenever any of the super translation charges or any of the large gauge charges are carried outward by Hawking quanta, it must react and correlate its quantum state. So what we now want to understand is how this process works in detail. And if we can see some amount of information coming out. Now, let me just summarize here. So we found a flawed assumption underlying the information loss argument. It could well be that this gives us some interesting nuance on how we think about this problem, but it may not be enough to solve it. So we haven't resolved the information paradox, but the nature of this flaw suggests a lot of interesting questions and phenomena that we can now start to investigate in a very concrete manner. So that is, now I'm turning to my recent work with Hawking and Perry. So what did we do? We tried to describe what happens when how a black hole carries is acted on by the supertranslation charge. So let me explain this picture. So here's the past, the far past, not much going on here. And then we send in a shell of matter, which we concentrate on a point, and the gravitational field gets very strong, and it makes a black hole, and you get what's called the event horizon, which is the boundary of the black hole. Everything in here is the black hole, and up here we have the black hole singularity. And once you get inside here, you can't get back out to future null infinity. Okay, so now I have not yet, this black hole, I'm not letting it evaporate just yet. That will be the next transparency. But let's now think about our conservation law. So our conservation law was an integral over this green surface. Before, we just had is equal to an integral over a red surface, which was future null infinity. Now we can complete this surface however we want. The identity will always be true. And so a good way to do it is go up future null infinity, but we need to close it off to use Gauss's law, otherwise we get an extra boundary term. And so we just continue around the event horizon like this. And then we use Gauss's law and integrate by parts, and we find that we get, here we had one strange duck, one soft photon, and here we'll have two soft photons, one term which creates a soft photon going out to null infinity, and another one which creates a soft photon, a zero momentum photon, along the event horizon of the black hole. What this operator does, just like acting on the vacuum, you created a soft photon, vacuum plus a soft photon. Here, if you act on the space-time with a black hole, you get a soft photon, an amplitude to create a soft photon which lives on the horizon of the black hole. This doesn't carry energy, but it's a new quantum state of the black hole, it doesn't carry energy, but it will carry angular momentum. So we can take the Schwarzschild black hole and we can add some angular momentum to it by doing this. And so that means that we have a degeneracy of black holes with the same mass, but different numbers of soft gravitons. That's what we call soft hair on black holes. Now, is this measurable? And the answer is, is this attribute of a black hole measurable? And there might be different ways that you might answer that, but an interesting way to address it is to say, all right, now let's allow the black hole to eventually evaporate. Let's turn on quantum effects. Now, we have an exact identity here, which is that if we take one of these conserved charges, we're integrating it over the sphere at the past to the future, we write that sphere as the boundary of this green space-like slice, which goes just under the horizon of the black hole, using Gauss's law, that's equal to the result that you get if you use Gauss's law in another way, which is that you just take the surface and put it through null infinity. Slide it up along null infinity. And we know exactly how this charge acts on the outgoing state at null infinity. And so suppose we have some quantum state on this space-like slice, which unitarily evolves to some quantum state on this space-like slice. And now we consider a new quantum state on the space-like slice that we get by acting with this charge operator. Well, since these two things are the same, the new quantum state, if we act with the charge operator before the black hole forms, that the result will differ by an action of the charge operator at future infinity on the outgoing state. So this gives us, and the black hole with the main difference here, and we can write this out in perturbation theory, and the main thing that this charge will do will create a soft, in this picture, the main thing that it does is to create a soft graviton on the horizon of the black hole. So if we know how a black hole evaporates, we have a deterministic relationship, in fact, an infinite number of deterministic relationships that tells us how a black hole with one soft photon hair evaporates. Okay, so I'm concluding now. So black holes carry quantum hair in the form of soft gravitons or photons, which arise from large gauge transformations or supertranslation. These carry some information about the quantum state of the black hole. And for reasons which I don't really want to go into right now, or I could, but I think it's unlikely that they store all of the information, that this is the end of the story. There are many more things that we need to take into account, other kinds of symmetries, the structure of infinity, and so on. I just want to say I don't think I think that this is a program which could lead to some complete story of black hole formation and evaporation, but we're very far from that now. And so whether or not we can get a complete picture of black hole information using these new insights is an interesting and very concrete challenge for future research. And thank you.
Very much. Questions?
So, in Maxwell theory, what would be the simplest observable, which is that soft photon?
Well, okay, so Yeah. So this bothered me a lot before I understood the memory effect. How do you detect a zero energy object? And the important thing is that these soft photons, the amplitude has a pole in it. And the Fourier transform of a pole is a step function. So when we do observations, we don't really do them in momentum space. We do them in position space. So what a soft graviton will do, and this is the gravitational memory effect, is if you have two inertial detectors, stuff comes by, then there's a shift. That's the step function. Okay? Now, the large gauge symmetries, and this is an odd difference between the electromagnetic and the gravity case, and perhaps why the gravity case was discovered before the electromagnetic case, is that in abelian gauge theories, there's also an interesting non-abelian story, but in abelian gauge theories, the symmetries are just phases. And so what will happen is if you have two objects, their phases will change. And we know that we need to do some kind of quantum experiment to detect relative phases. And there have been several papers on this. My favorite is actually a short note by Lenny Susskind, who had an array of squids and connected them with resistors and showed how you could measure these phases. Or you could just think about taking, two electrons with their phases aligned, pulling them apart, waiting for the large gauge transformation to occur, and then put them back together and see if their phases are aligned or not.
Infinity of some kind which you measure that, or what? I don't care about experimental device.
Oh, sorry. No, you don't care about experimental device. What I'm saying is that the phase space of Maxwell theory involves a point on a point on the sphere. You have to specify a gauge transformation. Those should not be regarded as physically inequivalent. Usually you would throw them out.
Okay, so that's a question of what kind of gauge group we divide by when we define the phase.
The flat connections on the sphere at infinity are physical. You have to specify a flat connection on the sphere at infinity. And that is a physical thing which has meaning.
Two-dimensional gauge field. Flat gauge field.
Two-dimensional flat gauge field. In fact, it's a U1 Kac-Moody. And those soft photon theorem is the Ward identity of a U1.
Kac-Moody problem.
Two black holes are merging. There are orbital angular momentum and spin angular momentum. What happened to the fractional part of the orbital angular momentum? If we believe that the final state of the merged black hole is still a good quantum number, good quantized number, and the total angular momentum is conserved.
Well, angular momentum turns out to be a very subtle concept in general relativity, and indeed, this was exactly where BMS ran into trouble. They were trying to define what angular momentum means in general relativity, because it has a very good meaning in special relativity. In fact, there is no canonical definition of angular momentum in general relativity. There's this much bigger infinite dimensional group called the BMS group, which was discovered by BMS in 1962 and then re-derived in 100 different ways over the intervening 50 years, and it's an infinite dimensional group, and the angular momentum is one, is somehow, you can only talk about that whole group. You can't point to a special subgroup of it and say that that's angular momentum. So this is very counterintuitive, and everybody thought that you know, general relativity should reduce to special relativity, and in some kind of long distance limit where gravity is weak. In fact, what I've just argued is there's an infinite amount of stuff at long distances in zero energy, and that is why general relativity doesn't reduce to special relativity. Special relativity doesn't have this infinite vacuum degeneracy in it.
So, as I know you know, the sort of traditional argument for the problem going back to Hawking involves this large buildup of entanglement between, you know, states inside the black hole and states outside. And the question is how you transfer that entanglement out. Now, what you're saying is that there's some large modification to that picture where you have this large.
There's a large modification to that picture. So,
let me finish.
yeah.
And because this is gravity, et cetera, but, you know, somehow we still, well, that picture, which is based on sort of a local quantum field theory description, is very similar to the kind of buildup of entanglement we might describe in other contexts with, say, quantum computers or whatever in other you know, quantum experimental situations. And there we don't expect there to be, you know, some huge modification, you know, enough to transfer entanglement from one place to another. So, you know, something has to be, in this context, especially pertinent to the black hole story that doesn't modify the usual story.
Well, quantum computers don't involve gravity usually.
Yeah, well, yes, they do, because they live in the real world, and, you know, Newton's is non-zero.
Gravity can be ignored.
That's a tiny effect, so why is it a big effect here for black holes?
Well, there are, I mean, I think we've unequivocally shown that there are an infinite number of correlations whose form and structure we can write equations describing between the quantum state of the black hole and the quantum state outside the black hole, to the extent that we can separate them. And that's another big issue, that it's not obvious that you can factorize the Hilbert space. So if you're asking me, Steve, how do I see to get from here to a complete solution of the information paradox? The answer is I don't know.
Well, if you can't separate them for a black hole, you might be worried you couldn't separate them for other situations, like, you know, in quantum experimental situations where you're doing something like building quantum computers.
Well, I'm sure those situations are all subject to these conservation laws and obey them.
Yeah, but we don't think they matter either in those situations.
We don't think what?
I don't think we consider them to be pertinent to what experimentalists do in the lab in those situations, or to the...
But there's no information puzzle with a quantum computer.
Well, there's nothing we need to solve there, and there's no solution. Now we have something we need to solve, and why do we think there's a solution?
Steve, I think you're arguing that the problem can't be solved and the universe isn't deterministic. I think you're arguing that the problem can't be solved. There's a solution there somewhere. We're learning some new facts. We're seeing where they're taking us.
So perhaps one last question.
So if the soft photon is a goldstone, is it still a normal photon? Because normally photon is not understood as a goldstone, right?
Sorry?
If the soft photon you talk about is a goldstone, is it still a normal photon?
Well, that's really a question of semantics. So if you have a, if you have a field in an upside down potential, the classic symmetry breaking story, and with some angle, you would say that the angular field is the Goldstone boson of the spontaneous breaking of the global symmetry. But actually, the only piece that enters into it, the only thing that transforms under the global symmetry, is the zero mode of the field. So the terminology is that when the zero mode of a field transforms under the symmetry, I don't know if it's a good terminology or not, but I think it's what people use, that we call the whole field the Goldstone boson of the spontaneous symmetry breaking. In the same sense, I could have said the photon itself is the Goldstone boson of spontaneous large gauge symmetry breaking, even though it's only the zero mode part of it that enters into the.
Okay, I think I can